Welcome to The Explainer. Today, we're going to decode the mathematical secret behind all the elegant, predictable patterns that are all around us. Let's dive right in.
Yeah, I know, it's a strange question, right? One's solid pavement, the other's, well, liquid. But stick with me because the answer reveals this really beautiful mathematical concept that describes so much of our world. Take a look at this example of fluid flow. This idea of smoothness is everything. It's a property we can feel and see. And today, we're diving into the mathematics that actually defines it, something called the analytic function. So, to really get a feel for this, let's start with a super simple everyday analogy. Okay, so picture this. You're driving on the most perfect road ever built. No potholes, no cracks, and absolutely no sudden sharp turns. Every single curve is gentle and predictable. Well, an analytic function is pretty much the mathematical version of that perfect road. It has no sudden changes. It's just perfectly smooth and well-behaved.
Okay, so the road analogy is great for our intuition, but let's move on to the actual mathematical definition. What exactly is an analytic function?
Now, the definition mentions differentiable, which really just means we can find its rate of change at any point. There are no sharp corners to mess up the math. The core idea, the really cool part, is this. You can zoom into an analytic function infinitely, and it will always look smooth. No hidden jagged edges, no matter how close you look. It's smooth all the way down.
But here's the thing. Not all functions are created equal. Take a look at the function on the left, z squared. If you were to graph that thing, it would be perfectly smooth everywhere. Now look at the one on the right, which has an absolute value. That function creates a sharp corner right at the origin. That single kink, that one point where it isn't smooth, is exactly what makes it non-analytic.
So you might be asking yourself, how do mathematicians actually test for this perfect smoothness? How do they know for sure if a function is analytic?
Well, they use a special condition called the Cauchy-Riemann equations. Now, you don't need to memorize these or anything. The crucial thing to know is that this is the mathematical test, the gatekeeper. A function has to satisfy these conditions to earn the title analytic. It's the ultimate check for perfect smoothness.
And this is where it gets really fascinating. This abstract mathematical idea isn't just stuck in some textbook. It shows up everywhere around us.
I mean, just look at this. The smooth, predictable flow of water in a pipe, or the way air moves cleanly over an airplane wing. That is a real-world manifestation of an analytic function. The system is well-behaved, with no sudden breaks or unpredictable jumps.
And the same math applies elsewhere. On the right, you can see a model of heat spreading across the surface. Notice that gradual change in color, representing temperature. There are no sudden hotspots. The heat just diffuses smoothly, exactly like an analytic function would predict.
And the pattern continues, even with forces we can't see. The shape of an electric field or the form of a pure sine wave both follow these same predictable rules. Analytic functions are like the invisible blueprint for some of the most fundamental phenomena in our universe.
Okay, let's wrap this all up and focus on the big takeaway. What's the main idea you should hold on to?
So why does all this matter? Well, because understanding analytic functions is like having a key to the underlying code of so many natural systems. It's the language nature uses to describe processes that are stable, predictable, and continuous. It's the rulebook for how things flow and spread and radiate in an orderly way.
In the end, it really all comes back to that one core concept: perfect, predictable smoothness. It's a function that behaves well everywhere you look.
And that leaves us with a final thought. If smoothness describes so much of our world, what happens when it breaks? That sudden change, the turbulence in water, a spike in a signal, that's often where the most interesting and sometimes the most chaotic science begins.